Welcome to today's library seminar titled Laser Spectroscopy for Trace Gas Sensing in the Atmosphere. I'm Lisa Clark, reference librarian at the NOAA Central Library. This presentation is part of the NOAA Innovators seminar series, which is put out by the NOAA Technology Partnerships Office. Tiffany House, commercialization specialist for small business innovation research, will introduce our speaker, Dr. Chris Hovde. Before we begin, here are a few logistical tips to help you enjoy our presentation today. If you're having any trouble with the audio or the visual components of GoToWebinar, please log out and rejoin us. This will usually resolve most technical issues. This presentation is being recorded and will be available on the NOAA Central Library YouTube channel, as well as the library seminars website later today. We will also be accepting questions throughout the webinar, which Chris will address at the end of his presentation. Please feel free to type your questions in the question box on the right side of your screen at any time. So with that, I thank you for attending this library seminar and turn the presentation over to Tiffany.
Thanks, Lisa. Welcome and thanks for joining us today. My name is Tiffany House and I have the pleasure of introducing the speaker and briefly describing the Small Business Innovation Research Program, or SBIR program for short. The mission of the SBIR program is to support scientific excellence and innovation through the investment of federal research funds in critical American priorities to build a strong national economy, one small business at a time. This is done through a competitive awards-based program known as the SBIR program, which enables small businesses to create innovative products and services for commercial potential. Southwest Sciences received a NOAA SBIR award in 2003, 2004, and 2016. The technology which will be highlighted today is available for phase 3, which means it can be acquired through a relatively easy process as a sole source procurement for NOAA or other federal agencies. This talk focuses on recent laser-based gas sensing developments at Southwest Sciences that grew from several NOAA-funded SBIR projects. In one project, techniques and instrumentation developed for eddy flux measurements were repurposed to show the proof of principle of a Mars rover that can trace gas plumes to their source using controlled releases of methane. The methane flux sensor is available from Southwest Sciences licensee. Also, Southwest Sciences developed a compact sensor for measuring flux of nitrogen dioxide from soils and agricultural sites. Dr. Hovde, hopefully I said that right, received his bachelor's degree in chemistry at Yale, his Ph.D. in chemistry at UC Berkeley, and then joined Southwest Sciences in 1990 after a post-doctoral appointment at Princeton. His research includes the development of laser-based methods for measuring fluxes and concentrations of trace gases. Ladies and gentlemen, it is my pleasure to introduce Dr. Hovde.
Thank you very much, Tiffany, for that introduction, and thanks for the opportunity to talk to everyone. I'm Chris Hovde with Southwest Sciences, and let's see, I think I'll get right to the next slide here. First technical difficulty, there we go. So I thought in one sentence what I wanted to encapsulate in this talk was that we're a company that commercializes, develops and commercializes laser-based diagnostics. And so the outline of my talk, I'll tell you a little bit about our company and how research focused we are with a little bit of manufacturing and then a stronger commercialization effort through our licensing to various companies. Then I'll tell you some about how the laser sensors work and what we do to get them to work well so that we can make the kind of measurements that are needed for various applications. And I'll go through some examples that are of interest, I hope, to the community. One is this methane sensor where we're where we kind of turned eddy correlation measurements on their side to try to look for the source of a gas leak. And another is a nitrous oxide sensor that's recently been used in field trials to measure fluxes at a site on a research farm in Michigan. So this is a picture from our 25th anniversary. The company was founded in 1985 by Joel Silver and Alan Stanton. And I kind of represented the current employees by these lines at the bottom of the slide. Alan and Joel are still active in the company. I'm the next longest line in the company, having joined in 1990. And in the mid-90s, I came to Cincinnati, Ohio for personal reasons, but opened up a remote office here where I've been working since. And the other employees are shown in this picture along with their families at the occasion of our 25th anniversary. And we've got, at this point, 6 PhD scientists and 1 master's degree scientist doing the research, and then a handful of support personnel doing the office work and the contract management kind of things. So it really is a small business, and it really is technology focused. We have over 30 patents. We have over 200 research papers. We have various active licenses that I'll talk about on the next slide. And in the past 15 or so years, 2 of our products, 2 of our licensees' products have won the R&D 100 award. Shown in the center picture is Mark Page holding the methane sensor that he really designed the optics and things for. The partner company, the licensee, designed kind of the framework for it and had the idea of the look and feel for that. That's a device that you can walk along and look for leaks in the natural gas pipeline system. It's handheld. The batteries are included in that thing he's holding. And so you can put it in the back of a pickup truck, drive somewhere, pull it out, walk along the line, find methane leaks from ambient concentrations, which are sort of in the part per million range, all the way up to 100% methane. And you might imagine when detecting leaks like that, it's important to have a sensor that's not going to cause the methane to explode. The old style of sensor was something based on a hydrogen flame. And if the signal got too strong, you had to quickly go put that away and get out a different kind of sensor to trace the leak all the way to its source, because the flame could ignite the methane. This one is all optical, and so there's no danger of that. And you can use it without ever having to go back to your truck for a second sensor. The second picture that shows an R&D 100 award is this methane flux sensor system that was commercialized by LICOR Biosciences. And that's showing a picture of a tower with some instrumentation on it, including the methane sensor in a field, probably in Nebraska somewhere. So yeah, our biggest effort at commercializing things comes from our licensees. And so I just wanted to walk you through a few of the various things we're able to do with this technology. To a company called Servomex, we license technology for detecting trace amounts of water vapor for the semiconductor industry. And so when you're making semiconductor chips with silicon and you're etching them, you don't want to have any water accidentally in some of the gases, because that'll form an oxide, which is silicon oxide, which is glass, which is an insulator. And so that ruins your chip. And so people install these things in the gases that they're using to monitor and make sure that the gas that approaches the semiconductor wafer as they're processing it stays free of moisture. And that can measure moisture levels down to a part per billion. So very, very dry trace conditions. In order to successfully commercialize that, you need salespeople who know how to go out and talk to people at the fabrication facilities of big companies like Intel, or at fabrication facilities in Thailand, et cetera. You also have to be prepared to service these instruments if anything goes wrong with them at a fabrication facility in Thailand or whatever. And so you can imagine that that takes more resources than a company of a half dozen people could provide. I don't want to jump on an airplane and fly to Thailand at a moment's notice, and they probably want somebody there quicker than we could get there from here. So that involves finding a partner, and Servomex is a company with an international footprint that can do that. LICOR Biosciences has a strong background in developing instrumentation for the environmental industry, and that includes devices for measuring carbon dioxide and water that are widely used in micrometeorological community. And we added to that by licensing to them this methane flux analyzer. They put a lot of engineering into that based on the designs we had, but then they added a lot of their own things to it, and so they've come up with an instrument that works unattended for long periods of time in the field. Here's the third one is a picture of the Hawk, the handheld methane sensor that's licensed to Southern Cross Company. And again, you need somebody who's got a sales crew that can go out to the various utilities and understands how that business works. And again, that's a completely different business from the semiconductor business. And then finally, this one on the right here is a picture of a device that is for the food industry. It measures how much moisture there is. You know, if you're making beef jerky or something, you want it to come out, you want your product to end up with the right amount of moisture in it, not too much so it goes bad and not too little so it's, you know, tastes like beef jerky or something. And so this is a device for measuring moisture in the air that lets them calculate how much moisture is in the product. And again, that's a totally different market than any of these others. We've got another license that's active that's looking at carbon dioxide isotopes in the breath from humans. It's for diagnosing certain illnesses where you can inhale a mist of some special chemical, and if you have certain types of diseases, you will breathe out a little more carbon-13 than carbon-12, and by measuring those isotope ratios, you can get some diagnostics on that. So again, these are all different applications, very different markets that we're able to address through this licensing strategy. We also have a commercialization business that is doing custom instruments and research and development services to people. And this is one particular example that I think is of interest to the atmospheric community and also kind of shows the ruggedness of this technique. This is the Gulfstream 5 research aircraft, and the little blue thing sticking up is shown in the expanded picture. That's something we designed that goes on the outside of the aircraft looking forward. And as the aircraft flies, air rushes back by that, of course, and the air contains water vapor. And so this is a way of measuring water vapor concentrations in the atmosphere. And this device can measure the water vapor concentration on the ground and where it's on the order of a fraction of a percent. And it can measure it all the way up to the stratosphere where the water vapor is a part per million. And of course, the density of the air is much lower at the troposphere, stratosphere boundary. And so it has a dynamic range to measure across that whole way. And this instrument has run on that aircraft for probably 10 years or more now. There's been some times when the mirrors needed to be cleaned. I know there was one runway where they were doing construction. There was a lot of cement dust that got on the mirror. But other than that, it tends to run without, you know, if you can keep the mirrors reasonably clean, you can use this thing for years with the calibration changing very, very little and the alignment staying intact through, you know, many, many, many flights. So this is an example that these can be rugged and work outdoors for extended periods of time. So that gives you a little bit of background of things. Now I wanted to focus a little bit on how the laser spectrometers work. And so I decided I was allowed to have one equation and maybe one or two spectra in this talk. So this is my one equation. I'm going to have it on the next 3 slides, but it's the same equation each time, just something different highlighted. So the sensitivity of the laser spectrometer depends on the wavelength in a big way. And I hope some of you recognize this bottom graph here is, I'm trying to highlight it with my mouse, and I hope that comes through. It's hard to tell since I don't have real-time feedback from you all. But this is the transmission of the atmosphere in the visible and infrared part of the spectrum. And of course, you can see that there's places that it's never 100% transmitting, but there's places where it gets down to 0%, and they get to be really strong in this mid-infrared region. Well, that's basically because there's gases that absorb infrared radiation in the atmosphere. The biggest one, of course, is water vapor, and the next biggest one is carbon dioxide. And those are the reasons for the greenhouse effect, is that radiation that gets emitted from the Earth gets absorbed by those and re-emitted in a way that reduces the amount of energy that's lost to space. And then sunlight pouring in gets absorbed a little bit in the visible and heats the heat, and a little bit in the infrared and heats the atmosphere. And so that causes changes to the atmospheric temperature profile. But anyhow, what I want you to get out of this slide is the idea that different molecules absorb at different wavelengths. And also, generally speaking, the longer the wavelength, the bigger the number of the wavelength in microns, the stronger that absorption is. And so this factor, this equation 1 says that the power that you get compared to the power that you transmit decreases exponentially as this function, which is sigma, which is a function of the wavelength lambda, times the number of molecules that are there times the path length it goes through. And so what I want you to get from this is the idea that if we pick the right wavelength, we can get a sigma that's a lot bigger than if we pick another wavelength that might be convenient for other reasons, but not because the molecule happens to want to absorb light there. And so a big part of how we've improved laser sensors over the last 20 years or 30 years of my career has been by other people developing lasers on our behalf. And when I started at the company, communications lasers were available, but only at one particular wavelength that wasn't particularly good for any of these gases, but worked okay for water vapor and a handful of others. As time went on, the number of communication lasers exploded. When the internet exploded, they developed something called wavelength division multiplexing, which meant they made lasers at a whole bunch of different wavelengths, and you could go out and buy them and be pretty sure they were going to be the wavelength you wanted. That opened up this band, this communications band, pretty strongly. But then later on, more lasers came out, and recently a type called an interband cascade laser, or ICL, is available. And typically, as these lasers get developed, at first the devices are kind of crude. They're simple structures that don't have any special structures in them to control the wavelength of the laser. It just demonstrates the laser can operate at a particular wavelength range. But as they've developed more, as they are more developed, structures are added on the wafer that control the laser wavelength to be a single frequency. And so these lasers I'm showing here are all at this point where they can operate at a single frequency. So you can turn them on, give them some electrical current, and get out light at a well-known wavelength. You have to control that wavelength. You control what laser you buy first and foremost, then what temperature you run the laser at, and what current you run the laser at, and you can get a wavelength of your choice. The next big factor in that equation is the path length L. And what we typically do is use something called a Harriot cell that gives a long optical path. And this picture with the green is a Harriot cell that was designed particularly for Raman spectroscopy, but I'm not going to get into Raman spectroscopy today. But the basic idea is a pair of mirrors can support a beam bouncing back and forth between it a large number of times. And if you're able to, stare closely at that picture, you'll notice that the green bow tie kind of shape is really constructed of lots and lots of rays of light bouncing back and forth. And I think that one has about 100 bounces or something like that between it. And so in this sort of half-meter long cavity, you can have something like 100-meter long optical path. So as far as the photons are concerned, they've had many, many chances to go past the atoms of the molecules of interest and have light absorbed. So the sensitivity gets increased by that path length. Now here I want to point out that there's competing techniques, and one of them is a technique called cavity ring down or cavity enhanced spectroscopy, because there's kind of a whole sub-genre of techniques associated with that. And in the cavity enhanced spectroscopies, instead of kind of injecting a laser beam into a cavity through a hole in the mirror like we do here, where you get a lot of light into the cavity, instead they shine light at a cavity that doesn't have any holes in it, and light builds up in the cavity if the wavelength is matched correctly, and then decays out of the cavity. And with good quality mirrors, the path length can even be longer. It can be up to, say, 5 or 10 kilometers. And so that gives real high sensitivity. The problem is, to get that sensitivity, the mirror reflectivity has to be like 99.999% reflective, which means that if you get any dirt on the mirror whatsoever, you can kiss that high reflectivity goodbye, and you suddenly have a much less sensitive technique. In our case, we really do send a ray of light into this thing and get that ray of light after it has made a certain number of passes. And so if the reflectivity declines, the power that we get out of the cavity declines, but the path length does not change. And so our sensitivity is independent of that. As a result, we can use these in an open path geometry where the mirrors are exposed, for instance, to the air that was rushing by in the airplane, or in other applications I'll show you soon. And the final factor I wanted to talk about was the noise floor. So in this simplified linearized version of the equation, I just express things as the change in a light power divided by the total light power is equal to this product of sigma times n times L. And if we can measure a real small change in light power, then we can measure a small amount of the molecules n. And so the way we do this is with a technique called wavelength modulation spectroscopy. And basically, these diode lasers, you inject current into them and they emit photons. And theoretically, you know, if life were perfect, you would have shot noise limited beam of photons coming out of the diode laser. And shot noise limited photons for the typical powers of this would mean you could detect changes in laser power of about 1/10⁷ or something like that. In fact, the lasers have something called 1/f noise, which is just a technical noise that tends to make the DC part of the laser power spectrum be much noisier than you'd predict from the shot noise spectrum. And so to get around that 1/f noise, we do something called wavelength modulation, and it simply consists of injecting an AC current into the laser and then taking the signal we detect and demodulating it at twice the frequency. And as a result, we get something that looks like more or less like the second derivative of an absorption line. And this spectrum here is an actual spectrum I took a week or two ago that shows that. So this is what would be an absorption line if you were to twice integrate it. And it has this sort of down, up, down, gull wing shape. This is actually another absorption line that looks similar to it. And then the reason I have the Where's Waldo picture there is that the noise is not set by white noise. Typically, it's actually set by something called an etalon fringe. Basically, any surfaces that reflect light and create a second path for the laser beam come back to interfere at the detector. And so it's kind of a coherent interference phenomenon. And what it does as a practical matter is it makes kind of a scallopy baseline in the signal that's not white noise. And it changes with temperature and it changes with other things like that slowly. So it's hard to calibrate out, but it's hard to, you know, you can't really average it away over short time scales, that kind of thing. And so it reminds me of Where's Waldo, and that, you know, really, it's not that hard to see a picture of Waldo on the page if there weren't all this other junk there. You would have no trouble picking out even a much smaller Waldo out of the page. But when there's all this stuff that looks like Waldo, he's hard to find. So anyhow, so in the same way, when there are all these kind of scallopy things in the baseline, as these signals get smaller, they get to be hard to find. So as a practical matter, if we design things well, we can detect pretty reliably laser power changes of about 1/10⁵. So that's still pretty nice, and that means we get a big dynamic range between seeing, you know, these fluctuations that are on the order of 1/10⁵ and 100% absorption. So we can see things over 5 orders of magnitude change in concentration of gas that way, and that's that's a lot of how the water vapor instrument gets its large dynamic range. So those are my 3 slides on how this stuff works. So now I want to talk about an application. And a number of years ago, somebody at NASA thought they saw a burst of methane on Mars. And people know a lot about atmospheric chemistry, of course, and they know the destruction mechanisms of methane in an atmosphere. They know it in Earth's atmosphere pretty well, and they think they know it in Mars's atmosphere pretty well. So if they had this large concentration on Mars, it meant there had to be a large source. Well, then the signal went away, and for a number of years, it went away for a number of years, I think, and people started wondering if it was real. But then one of the rovers found methane again on Mars with similar kind of dynamics, where it peaked up to a fairly high concentration and then went away again. And so there must be some kind of source on the surface of Mars that's producing methane. And that would be really exciting. Even if it was just a geological source, it would be very interesting. And of course, if it's a signature of life on Mars, then that would be super, super interesting, because to have detected life on another planet would be like a really, really major scientific breakthrough. So, so I worked with a group of other people to sort of dummy up something that would look more or less like what a rover would look like, a real, glue and baling wire kind of version of a Mars rover. And so, and then try to find methane leaks on Earth's surface. And so the idea is that from orbit, you might be able to locate the source of a methane emission to within, I don't know, maybe 10 kilometers or something like that. But to really find the spot it's coming from would take a rover on the surface that would have to find its way. And so this thing here would be to, how to teach the rover to find its way to a Mars methane source. And so it has 2 things that are familiar to a lot of atmospheric scientists. It has this open path methane sensor, and this was the same sensor that was licensed to LICOR Environmental and won an R&D 100 award using the technology originally developed at Southwest Sciences. And then it has a sonic anemometer, which measures wind speed in 3 directions, so we can get east, west, and up, down winds, and north, south, east, west, and up, down winds. And the whole thing is mounted on a pole that's mounted on a trailer hitch, because I knew I was going to have to take this to Idaho, where I would have to rent a vehicle. I didn't want to have to drive a custom van out to Idaho to test it. And so I thought, well, I know I can get a trailer hitch on the back of a pickup, so let's build it off of that. I think I am not as good of an engineer as I am as a laser optics person, so it had a lot of sway to it when it was driving around. I don't recommend that as a final design for how to mount things, but let me tell you a little bit about this LICOR methane sensor. So basically, they fold a 30-meter path into about a half-meter long air gap, and they do wavelength modulation, and as a result, they can detect methane down to about 5 parts per billion. And for reference, the background level in the atmosphere at a clean site is about 1.6 or so parts per million. So, factor of several hundred more than this noise floor. So we can detect methane with signal to noise of several hundred. And the measurement range for this instrument, they can go as high as 25 ppm. In fact, in the tests I'm going to show you that we did, it went even beyond that, and I was able to recover some signal by looking at the data and hand analyzing some of the data that they have that they don't typically do. So I was able to get another probably 10 or 15 ppm of dynamic range out of the system. The whole thing takes less than 10 watts of electrical power and weighs a few kilograms. And the whole thing is basically this tube thing that sticks on the top of the tower that I showed you on the previous thing. This is the methane sensor in its entirety. There's no big electronics box sitting down below it to operate it or anything like that. And then it has Ethernet communications, and it has inputs for analog measurements, and LICOR figured out how to make the mirror spin, so if it got any water on it, you could spray a little window cleaning fluid on it and then spin it real fast, and that would come off along with the dirt, and then the mirror would stop and the whole thing would be aligned again and ready to go. So LICOR put a lot of effort into making this so it really is an instrument you could put out in the wild and not have to come by every day and babysit. So we took this plus the Campbell Scientific wind sensor to the desert in Idaho National Labs in central Idaho. And I was working with Don Banfield at Cornell and Brian Lamb at Washington State and Tom Ferrara at GHD, which is a consulting company that does environmental measurements. And Tom has a van that's outfitted with a methane sensor and wind sensors and things like that he drove cross country to participate in these tests also. So the basic idea is we put a cylinder with methane and we crack the valve on the cylinder to release methane at a known amount per unit time. And then we park the truck someplace away from that and try to measure methane in the atmosphere as well as wind. And from those two measurements, over a period of time, build up an idea of where we think the sensor location is. And you can easily imagine getting a heading to the sensor by just saying, well, the most likely thing is when the wind blows from the direction of the source towards my detection point, that's when I'm going to see the biggest concentrations of methane. And that, in fact, does work, and that's how you get the heading. But getting the range is a little more subtle. But if you think about this, like if you imagine a smokestack and the plume coming from the smokestack gradually getting bigger and bigger, what that means as it gets bigger is that when the wind makes small fluctuations, it doesn't cause as much change in the concentration. And so, what Don Banfield did was he incorporated a SciPuff model for atmospheric transport with the measured wind field, and he evaluated that model and at each of these triangular points. And basically, the bigger and brighter the triangle, the more likely it is that model gave rise to the data we observed. And when he does that and picks out the one with the best, it is this green square that's almost right on top of the actual source at this distance. And so we can get the location of the leak pretty accurately that way. I should mention that this assumes that there's one leak. And obviously, if you go to methane, no one promises you that it's only going to leak out of one spot in the ground. It could be, various things, or it could be, a area source or something like that. And so I think we need to, maybe do more stuff to understand what happens in those situations. But you can imagine a Mars rover starting from a distance could gradually work its way back towards a place that seemed geologically interesting because it was a source of methane. And then this brought up a potential commercial opportunity, and we've talked to one major energy company about this, which is that fracking, is a new technology that has generated a lot of oil and natural gas for the United States, but it also releases some natural gas. And of course, methane, the main thing in natural gas, is a potent greenhouse gas. And so the idea was, hey, if we can figure out where the leak is, then you guys can fix the leak and reduce the amount of natural gas being emitted to the atmosphere. And this seems really smart as a way to reduce the carbon footprint, because here you have something that's 100% methane. I mean, what could be better than that, right? If you go to a coal-fired power plant, you're looking at, coal mixed with water vapor and nitrogen as your starting mixture. Here you've got something that's a lot closer to 100%. And not only that, methane is a more potent greenhouse gas than carbon dioxide. And not only that, when you capture the methane, you can sell it. So it really seems like a great, win-win-win kind of thing. And furthermore, it turns out most of the wells are pretty good. A lot of the methane that's getting emitted is by a very small fraction of the wells. So if you could go and find the bad wells and fix them up, you could fix a lot of the problem of methane being leaked out as a result of fracking. But these are two screen grabs from the New York Times, one in 2015 and one in 2019. and there's just as much political winds as there are, weather winds. And so the U.S. policy towards, requiring industries to reduce the emission of greenhouse has changed about 180 degrees over that 4-year time frame. So it's not obvious to me that industry is going to do this unless the amount of money they could make by reducing the leak is enough to offset the cost of finding the leak. And that would have to include, the cost of fixing the leak and that kind of thing. So barring regulations, it's not obvious there's going to be a strong push by industry to adopt something like this. So now I want to switch from methane to nitrous oxide, which is another potent greenhouse gas, and it's also part of the nitrogen cycle. And so Southwest Sciences got funding from NOAA and then more recently from Department of Energy to develop nitrous oxide. I always get my oxides confused. And again, it's using this open path design. So the mirrors are exposed to the atmosphere. That means gas can flow in and out very easily without the need for a vacuum pump or anything. And as a result, we can get real low power operation and lightweight and all those kind of nice factors. And this shows some lab testing that here's a part per billion at the top of the scale, and the noise is dropping off with integration time so that at 10 hertz, it's on the order of 0.1 parts per billion. And this is done jointly with Mark Zondolo at Princeton. Mark used to be a scientist at Southwest Sciences before he left the commercial world to become an academic. And so this was a project where we had the opportunity to collaborate with him closely. And it was really valuable because he has a much stronger field testing capability than we have. And, and he has the benefit of graduate student labor, which fits onto a contract a lot more nicely than PhD labor for doing field experiments. And again, the design is similar to the methane thing I showed you. This shows things opened up a little bit, but there's some multipass optics on the left-hand side of this picture, and then there's the laser and some optics for launching the laser and detecting it, and some electronics that I don't think you can see. They might not have been installed when this picture was taken, but anyhow, the electronics fit in there too to operate the laser. And then this picture in the center is a detail of what this pattern of spots looks like on the mirrors. This was something we came up with, Joel Silver at our company came up with, that lets the spot density be higher on the mirror so we can get, for the same diameter of mirrors, we can get a lot more passes in. So that keeps the instrument size smaller and lighter and that kind of thing. And it shows you that each of those spots represents, one time that the laser went out to the mirror, hit it, and came back. So we can get quite a few passes between the two mirrors. The custom electronics we've developed over the years. I have a strong memory of the NOAA-funded project back in the early 2000s of working on the software for that while my son was at a skate park in Louisville, Kentucky, skating on half pipes. And I was, sitting there, having driven him there, working on the code for this thing. Anyhow, an embedded microprocessor and then analog electronics and digital to analog converters that allow us to drive the laser current, modulate the laser current with this sine wave that we need to do the wavelength modulation detection, do regulation of the laser temperature to around 1,000th of a degree using what's called a thermoelectric cooler. Those are built into the laser in most modern lasers. And then capture the data digitally and then use fitting algorithms to extract concentration signals from that and finally have a serial output. And so that all fits onto this thing that's, a few centimeters in one dimension and, 10 or 15 centimeters in the other dimension, and is in the handful of watts power range. So here's the mechanical specifications. When we started doing this project, we thought we were going to use something called a quantum cascade laser. And quantum cascade lasers, I guess the cascade name refers to it's got a lot of layers and that things jump between. And so it's kind of like lots of little waterfalls that electrons make as they go through it in order to make photons. And they tend to require a lot of power. And so when interband cascade lasers came along that needed quite a bit less power, you can see in this column 2.5 watts for the quantum cascade laser versus 100 to 200 milliwatts for the interband cascade lasers. We kind of switched the project to using interband cascade lasers. The other thing was that we were going to need an external electronics box that was going to be pretty big, a 20-pound box holding the electronics for the quantum cascade laser. When we switched to the interband cascade laser, we were able to get rid of that and just put our little circuit board into the optical head. It made the optical head slightly bigger, but that's about it. So the whole thing is under 10 watts. And just to give you some point of reference, I went on to eBay this morning and cut out this little picture. For under $30, you can buy a 10-watt solar generator. They're not super big, and you probably need 2 or 3 of them if you're really going to run this 24/7, because you'll want it to run at night. So you have to have 20 watts during the day so you can be running it plus charging a battery at night. And then you might want a little engineering headroom for cloudy days and all that kind of stuff. But the point is, for $100, you basically can take your power source anywhere you want that the sun shines in the world and operate. You would have trouble on the Arctic in the winter or something like that, but you really are, for certainly most continental locations, you're free to run for long periods of time at this kind of power budget. And so that's important for working remotely. If you're restricted to sites where you have a power line pulled to the site, or you're able to, keep a generator running with gasoline or something like that, then you've really narrowed down the list of places where you can do field work. So this thing liberates you from that. The spectrum was stable versus time. This is kind of a colorful plot that's probably hard to interpret, but basically the idea is the red colors represent the way this signal gets sort of tall, and the blue colors represent where it's down near the bottom, and the green is kind of where it's at the middle here. So and each one of these pixel slices here is a particular measurement. And so this just lines up a whole bunch of measurements that all look more or less like this basis vector that we use to fit the data. And so the point is that for this 120,000 averages, or not averages, 120,000 spectra, we get spectra that look pretty much the same all the time. It's hard to compare them in a 2D plot like that, so the color plot lets us kind of show that. But the system seems to be very stable. And so Mark Zonderlo took this to a field site and worked with some professors at Michigan State, and that's the Kellogg field site. And I think it's actually a cornfield, which, given Kellogg's background in cornflakes, kind of makes sense. And so in the summer of 2015, you can see there were some significant stretches where things didn't work. In the summer of 2016, it was working closer, looks like upwards of 50% of the time. It'd certainly be nice to continue to improve that and get it up to 100% of the time, but it's certainly something that was operational for large stretches of the summer of 2016. And also nicely, this chart shows that the noise was comparable to the noise we saw in the laboratory. So we're doing better than a tenth of a part per billion at, about a tenth of a part per billion at 10 hertz, and then a little better than that at longer integration times. And finally, I wanted to kind of wrap things up by telling you that these devices work by spectroscopy, and spectroscopists have been busily measuring the coefficients and wavelengths and things like that needed to predict the sensitivity for a long time. And so these numbers are well known. And this chart kind of gives you some ideas for various things of what wavelength you would need and what kind of sensitivity you could expect if you had a 30-meter path. And so the sensitivity can be really pretty phenomenal. I must have rounded off too much when I put 0 for carbon dioxide, because I'm sure it doesn't go all the way down to 0, but it goes down to a pretty low level. And so it's possible to design sensors to work on all these things. So what I wanted to conclude was takeaway messages. One is you can get compact sensitive instruments based on laser-based spectroscopy. I think something that can go on the back of a pickup truck and drive around and be working is reasonably rugged, and something that can go on an airplane and fly for 10 years is pretty rugged. Then the combination of wind measurements plus the gas measurement gives you a lot of capabilities, and eddy correlation measurements are a well-known one where you can measure the flux of gases, but also this plume tracing where you can find sources is another possibility. And finally, I want you to realize that you know, the list of gases is pretty much anything infrared active that's a small molecule. And that concludes my talk. So I guess I probably need to talk to Tiffany or Lisa to open up this to questions now. Thank you for your attention.
Thank you, Chris. I really appreciate your presentation. This is Lisa speaking. Audience, we do have some time for questions. So I encourage you to type them up in the question box on the right, and I will read them to Chris. We did receive one question during your presentation, so we'll start with that, Chris. This person asks, how well will sonic anemometers work at the 6 HPA surface pressure of Mars?
We're actually working with another company on sonic anemometers for Mars combined with a water sensor for Mars. I'm not sure how well it's going to work. I guess I don't know the detailed technical specs, but yeah, the pressure on the surface of Mars is very low, but people are working on that. So there is development on that. And Don Banfield, who I worked on with the Mars measurement, is also working with us in that project. He's got some expertise in sonic anemometry too. So I don't think it's technically impossible to do it. I do think people are, you know, people who have expertise in that are working on it. I don't know much about the anemometry physics to know how, you know, what things are tough to do about that. But it is going to, there is a vision for an anemometer plus a sensor, and I think the anemometer is something we've already worked on integrating with a gas sensor with an anemometer.
Great, thank you. I'm going to give us another minute or so to see if there are any more questions. And again, to the audience, this is a great time to talk directly to Chris. So if you have any questions, please write them in, or type them, I should say, in the chat box on the right that says questions. Meanwhile, I just want to remind people that this webinar was recorded, and we encourage you to share the link with interested colleagues or watch the beginning of the presentation if you joined us late. You can find the recording on the NOAA Central Library YouTube channel or the Library Seminars webpage by the end of the day. It's a little, sometimes it takes a little time, so I'm going to give it another minute. Oh, there's another question here. What is the R&D 100 award? You said you won it twice.
Go ahead.
Sorry. So no problem. How does a small business find out about these awards?
The R&D 100 award, I think there's an R&D 100 organization that gives these awards out. I think that in both cases, it was our licensees who kind of shepherded the application through. But small businesses can apply for them. Government labs can apply for them. Yeah, it's a reasonably prestigious award that is given to new technologies every year. 100 new things every year. I think that's the source of the name. And they can span all range of new useful things. So it's not limited to, you know, atmospheric science or something. But I attended the award banquet the year that the methane sensor for atmospheric science was awarded, and it was, you know, put on a tuxedo and all that kind of stuff, which I hadn't done since high school prom, I guess. But yeah, it was just a real wide variety of people doing all sorts of different things. So I would encourage Googling R&D 100 application or something and see what turns up. I think you
Great.
self-nominate as you know, so you send in your application materials to a committee that then picks things out. I don't think you wait for somebody to nominate you.
It's interesting, actually. There is another question here. This person asks, can interband lasers be used to make a low-cost RH sensor that can work to 1% accuracy, fast time response in ocean unattended applications?
So let's see. Can they measure moisture? Could you read the question again?
Sure, of course. Can interband lasers be used to make a low-cost RH sensor that can work to 1% accuracy, fast time response in ocean unattended applications?
Okay, so first of all, the low cost part of it, depending on the laser, some of these lasers are several $1,000s. Some lasers are much cheaper than that. Obviously, everyone here is familiar with compact disc lasers, unless you're so young that you never knew anything but an iPod. So those lasers, the compact disc player type lasers are a few dollars each. I've worked spectroscopically with a type of laser called a vertical cavity laser, which is a pretty low cost format. So it's possible to use vertical cavity lasers to measure water vapor. So RH is relative humidity, right? Another part of the relative humidity thing is getting the temperature pretty accurately. And so that our sensors tend to measure the concentration of the gas, the absolute humidity, as opposed to the relative humidity. So I would have to think about whether that could hit to 1%. And then certainly the ocean environment, the unattended ocean environment is a pretty tough environment. I have not built anything that that goes out in the ocean, so I'm not super familiar with that. But I do know it has its challenges. So it'd be interesting to talk more about, I guess, in terms of what the budget was for it and that kind of thing. The fast response, yes, I definitely think it could be fast response. Depending on the laser wavelength used, it could be that it doesn't need this multipass optics, which would make the ruggedness factor go up, because now you're just talking about we somehow have to get the light to go through the atmosphere and then back onto the detector and we're done, instead of bounce around 100 times. Because presumably the water concentrations are going to be a lot closer to 1%. I mean, I guess if you're someplace cold, the concentrations will be lower, but still a lot higher than they are in the stratosphere. So, yeah, I'd say it's possible to, find something that's going to be low cost. It's possible to find something that's going to be fast and all that kind of thing. Whether that intersection is going to include everything you need or not, I'm not sure, but it'd be interesting to talk more about that. So my email is on the first slide, and I'm happy to scroll back up and make sure that ends up there. And I'm also happy to take phone calls about things like that. So, and I've got a very Googleable name. So,
there's actually two more questions. One's very straightforward, which I think I can answer. It asks, will slides be available after the presentation? The answer is yes. If you contact the library at library.seminars, that's plural, at noaa.gov, we can send you the slides from today. And then the last question I have here, is, you were awarded this phase 2 in 2003. How has the technology evolved since then? Did you have to shift your processes? You may have mentioned this already.
Yeah, the technology has definitely evolved since then. For instance, the earlier versions of the electronics board that I was programming while my son was skateboarding, we've gone through a number of iterations of improving that. So it's now 16 bits instead of 12 bits and can support multiple channels and things like that. The laser technology has improved. I did talk about the one project where we started out thinking we're going to use a quantum cascade laser, but the interband cascade lasers came along and elbowed it out of the way because it worked, with such improved specs in terms of power and that kind of thing. So the technology is constantly evolving, and we're trying to stay up with that and incorporate the latest lasers and that kind of thing. So what I tried to give you today was a flavor of where we are in 2020 that grew out of the work we did in the early 2000s. So, so yeah, it was quite a bit different then.
Excellent. It looks like that might have been our last question today. So I'm going to go ahead and conclude our webinar. I'd like to thank our speaker, Dr. Chris Hovde, for sharing your experience with us, and to Tiffany House for organizing today's Innovators seminar. And to the audience, I truly appreciate that you joined us for today's library seminar. NOAA Central Library is very proud to present the work of the NOAA community and its partners, and we hope that you will join us again. Be well, everyone. Thank you, Chris.
Thank you. Bye.
Bye-bye.